So first of all, a graph can be interpreted as a design in such a way that we take the vertices of the graph as points and the neighborhood of the vertices as blocks. That means actually that we look at the adjacency matrix of a graph as the incidence matrix of a design, which is called the neighborhood design then. So if we have a k-regular graph on V vertices with the property that any two distinct vertices have exactly lambda common neighbors, this graph is called a VK lambda graph. Actually, this is a strongly regular graph with parameters VK lambda, and it is well-known connection with between these graphs and the symmetric designs. So the neighborhood design of VK lambda graph is actually a symmetric VK lambda design. First of all, I will mention this definition from the paper from 2011 by Hamers Haragani and Willem's student, as I know, Muhlenberg. This is definition of a divisible design graph, which is actually generalization of VK lambda graph. So a k-regular graph on V vertices is a divisible design graph, or DDG for short, with parameters VK lambda 1, lambda 2, Mn. Whenever the vertex set can be partitioned into M classes of size n, such that two distinct vertices from the same class have exactly lambda 1 common neighbors, and two vertices from different classes have exactly lambda 2 common neighbors. So, and why it is generalization of VK lambda graph? If in a DDG we take if m is equal to 1, or n is equal to 1, or lambda 1 is equal to lambda 2, then DDG is actually a VK lambda graph. In this case, we call this DDG improper, otherwise we call it proper. So name divisible design graph comes from the fact that it is actually divisible design, which is at the same time a graph. So this is definition of divisible design. An incident structure with V points and a constant block size K is a divisible design, or sometimes called group divisible design, with parameters VK lambda 1, lambda 2, Mn. If the point set can be partitioned into M classes of size n, such that 2 points from the same class are incident with exactly lambda 1 common blocks, and 2 points from different classes are incident with exactly lambda 2 common blocks. Such divisible design is said to be symmetric, or to have the dual property, if the dual structure is divisible design with the same parameters as the original divisible design. And it is easy to see that the neighborhood design of a DDG is a symmetric divisible design, and so every DDG is a symmetric divisible design in a way, and conversely, a divisible design admitting a symmetric incidence matrix with zero diagonal is the neighborhood design of DDG. So this is a structure introduced 10 years ago by Hadi and Willem and Willem's student. So I will talk about Cayley graphs. Also divisible design Cayley graph. So this is definition of a Cayley graph. If G is a finite group with the identity element E, and S is a subset of G, which is closed under inversion and doesn't contain the identity, then the Cayley graph GS is a graph with the vertex set G, and two vertices X and Y are adjacent if and only if the product X time inverse of Y is in S. Now this is a well-known structure, and Kavanov and Shalaginov studied the divisible design Cayley graphs in this paper, which is accepted for publication in the Art of Discrete and Applied Mathematics. So well-known theorem from 1958 by Sabidussi says that a graph gamma is Cayley graph if a group of some group, if and only if automorphism group of D, it's a mistake, it should be gamma here instead of D, contains a regular subgroup. And Kabanov and Shalaginov gave this theorem in that paper which I mentioned on the previous slide. So let Cayley graph GS be a digraph with parameters, I think that all of you know what digraph is, with parameters Vk be A, and S times S to the minus 1 equals A times A plus B times B plus K times E, where A, B, and identity element is a partition of group G. If either A together with the identity element or B together with the identity element is a subgroup of G, then this Cayley graph GS is a DDG, and the right cosets of this subgroup give a canonical partition of the graph. And conversely, if Cayley graph GS is a DDG, then the class of its canonical partition, which contains the identity of G, is a subgroup of G, and classes of the canonical partition of DDG coincides with the cosets of this subgroup. So, Kabanov and Shalaginov gave this theorem in that paper, and also gave a nice construction of the divisible design Cayley graphs, which comes from finite fields of order Q to the R, where Q is a prime power and R is greater than 1. And this construction so is based on this theorem that they gave also in that paper. I will now present some constructions of Cayley DDGs, which are based on the constructions of DDGs, which are presented in these two papers. So first is that paper where the authors introduced divisible design graphs. First of all, this is one obvious construction. If A is an incidence matrix of a VK lambda graph with a regular automorphism group G, then there exists a divisible design Cayley graph with parameters V times T, K, lambda, 0, T, and V. How we can obtain such a structure? So we just take a canonical product of identity matrix with matrix A. And it is easy to see that this is adjacency matrix of a DDG with parameters V times T, K, lambda, 0, T, V. So this is a DDG. Now we have to conclude that this is a Cayley. This is a Cayley DDG, Cayley graph. And we will conclude it by finding a regular automorphism group, and it is also obvious that a direct product of the group G, which is mentioned in the theorem, and the cyclic group of T elements acts regularly on this DDG. And by that Sabidussi theorem, the constructed DDG is a Cayley graph. Actually, in the proof of this theorem, instead of the identity matrix, we can use any symmetric permutation matrix P. The second construction is also obvious. So we have a incidence matrix A of a VK lambda graph, also with a regular automorphism group G. Then there exists a divisible Cayley graph with parameters V times N, K times N, and K times N. So lambda 1 is equal to K. And fourth parameter is lambda times n, and then v and n. So how can we construct such a structure? Also, I said that this is also obvious construction. We just take a canonical product of a matrix A with O1 matrix, and this is obviously adjacency matrix of DDG with these parameters from the theorem. And also it is obvious from the construction that this DDG admits a regular action of the direct product of the cyclic group of order n and the group G, which acts regularly on that graph that we started. And again, by substitution theorem, this is a Cayley graph. Okay. Also, one theorem that comes from construction from that paper by Hadi and Willem. The strong product of two graphs with adjacency matrices A and B is the graph with adjacency matrix. So it's canonical product of A plus identity matrix and B plus identity matrix, and then we subtract identity matrix from that canonical product. We have the following theorem. Let gamma be a strongly regular graph with parameters m, k, lambda, lambda plus 1 with a regular automorphism group G. Then the strong product of k with gamma is a Cayley DDG with parameters 2 times m, 2k plus 1, 2k, 2 lambda plus 2, m2. And again, the proof of it's obvious that we have regular group acting on this design. So again, by substitution theorem, we know that that this is a Cayley graph. And so we need, for this construction, we need strongly regular graphs with these parameters. So strongly regular graphs where mu equals lambda plus 1. So it is one well-known family of strongly regular graphs with this property. And these are Paley graphs. So this is a Paley construction of Paley graphs and Paley designs. So if Q is a prime power, which is odd prime power, then if Q is congruent to 3 modulo 4, then the set of non-zero squares in the field of order Q forms a different set in the additive group of the field. And in the case when Q is congruent to 1 modulo 4, then the set of non-zero squares in this field forms a partial different set also in that additive group of the field. And in both cases we have Cayley structure. So if Q is congruent to 3 modulo 4, then we have a Cayley digraph. And in the case when Q is congruent to 1 modulo 4, then we have a Cayley graph. Actually, the adjacency matrix of that Cayley digraph, it is well known that this is identity, that this is a incidence matrix of symmetric design with these parameters Q minus 1 over 2 and Q minus 3 over 4. And such a design is called the Paley design. And
Odin, may I ask you a question? Yeah. Well, because on this slide, you call Paley design, and this Paley design corresponds to Cayley digraph, right? Yeah. So, but is it possible to define a Paley design which will be correspond to just Cayley graph, not digraph?
To Cayley graph, actually it is not. We can define design, but then it is not two design. This is just one design. So, so because in that case, when we have a Cayley graph, then we get a strongly regular graph with these parameters Q minus 1 over 2, Q minus 5 over 2, and Q minus 1 over 4. So if we take, if we look at adjacency matrix of that graph. So 2 rows or 2 columns, it's the same, have actually 2 intersections, q minus 5 over 4 and q minus 1 over 4. So this is a symmetric design, but not 2 design, just 1 design, which is actually less interesting than 2 design. Yeah. So that's why by the name Cayley design. So just this first structure, this Cayley digraph, is actually known as Cayley design. And in the second case, we get a strongly regular graph, which is then called Cayley graph. Yeah. Okay. Yeah, and so we see that Cayley graphs belong to the family of SRGs with parameters Vk lambda lambda plus 1. So there is that mu is equal to lambda plus 1, and so we can then apply. We can just use Cayley graphs in that construction from that previous theorem, and we get the following corollary. Let Q be a prime power, which is congruent to 1 modulo 4. Then there exists a divisible design Cayley graph with these parameters. So this is just we just plug in Cayley graphs in that construction from theorem 5. Yeah, and Cayley construction is actually closely related to Adamar matrix, Adamar matrices. So what is Adamar matrix? If we have a m times m Adamar matrix H, it is called Adamar. If entries are plus and minus 1, and H times H transpose is equal to m times identity matrix. So it is well-known Adamar conjecture that such matrices exist for all positive integers which are divisible by 4. So, and as Hadi would probably say, that we are very far from proving that conjecture, and well, I agree, of course. Adamar matrix H is called graphical if it is symmetric with constant diagonal, and it is called regular if all rows and column sums are equal, and for example, let's say equal to L. Without loss of generality, we can assume that the graphical Adamar matrix has diagonal entries equal to -1. So we can assume that because if all entries are equal to 1, then we can multiply by -1 every, for example, row, and we'll get such a Adamar matrix with diagonal entries -1. So let us consider a regular graphical Adamar matrix H. It is well known that L square is equal to M, and that 1/2 times H plus all in one matrix is the adjacency matrix of a strongly regular graph, which is with parameters m plus L over 2, m plus 2L over 4, and mu is equal to lambda, also m plus 2L over 4. And we have the following construction. So let H be a regular graphical Adamar matrix of order 4U with diagonal entries -1, and the row sum 2 times U, where U can be negative. And let us assume that such a matrix have a regular automorphism group G. Further, let D be the adjacency matrix of nk prime lambda graph with a regular automorphism group G1. So if we replace each entry -1 of H by D and each entry +1 by all one matrix minus D, then we obtain the adjacency matrix A of a Cayley DDG with these parameters. I will not read all of that. And how can we prove that? So by straightforward verification, we can we can check that this is a JCC matrix of a DDG. So we use properties of Adamar matrix and properties of that strongly regular graph. So now we know that this is DDG. We have to conclude that this is Cayley DDG, and we can just observe that direct product of G and G1 acts regularly on that DDG. So again, by Sabidusi theorem, this is a Cayley structure. Okay, so now I will switch to Cayley digraphs. We call a digraph D on V vertices doubly regular with parameters Vk lambda if it is regular of degree k, which means that all in degrees and all out degrees are equal to k. And any distinct vertices x and y, for any distinct vertices x and y, the number of vertices z that dominates both x and y is equal to lambda, and the number of vertices z that are dominated by both by x and y is also equal to lambda. So such structure is doubly regular digraph. The JCC matrix of a doubly regular digraph is an incidence matrix of a symmetric design. This is also known. And the digraph D is asymmetric if the fact that we have an arc from x to y implies that we don't have an arc, opposite arc. And this is definition of divisible design digraph from this paper with Hadi from 2015. Let D be a regular asymmetric digraph of degree k and with V vertices. D is called a divisible design digraph, or DDD for short, with parameters Vk, lambda 1, lambda 2, Mn. If the vertex set can be partitioned into M classes of size n, such that any two distinct vertices x and y from the same class, the number of vertices z that dominates or being dominated by both x and y is equal to lambda 1. And if we take vertices from different classes, so again vertices x and y, then the number of vertices z that dominates or being dominated by both x and y is equal to lambda 2. So this is actually a natural definition of such structure. So that's the DDD. DDD is a natural generalization of doubly regular asymmetric digraphs. The JCC matrix of DDD with M equal 1 or N equal 1 or lambda 1 equals 2 is the incidence matrix of a symmetric design. And in that case, we call that DDD improper. Otherwise, we call it proper. Again, we'll just take a look at neighborhood design. So if D is divisible design digraph with parameters Vk, lambda 1, lambda 2, Mn, then its neighborhood design is a symmetric divisible design with the same parameters. So now we'll say when we will call a matrix Q. So we say that 0, 1 matrix X is Q if X plus its transpose is a 0, 1 matrix again. So thus the JCC matrix of a DDD is Q by this definition. If D is a symmetric divisible design with parameters Vk, lambda 1, lambda 2, Mn that has a skew incidence matrix, then D is the neighborhood design of a divisible design digraph with the same parameters. And now this is the definition of a Cayley digraph. So let G be a group and S a subgroup of G, which don't contain identity element of the group. And we call that identity element E again. The vertices of the Cayley digraph GS are the elements of the group G, and its arcs are all the ordered pairs G, GS, where G is from the group G, and S is from that subset capital S. And also we have a theorem which is similar to Sabidos's theorem that I presented previously for graphs. So a digraph D is a Cayley digraph of a group if and only if automorphism group of that digraph contains a regular subgroup. So again, we will look for regular subgroups of structures that we construct. So in the sequel, I will present results that are given in this paper with Hadi and Andrea. So here we have this theorem, which is very similar to theorem given by Kabanov and Shalaginov that I mentioned at the beginning of this talk. So let Cayley graph GS be a digraph, and S cardinality of S is K, and intersection of S and S to the -1 is empty. And let us assume that S times S to the -1 equals A times A plus B times B plus K times identity element, where again A and B and identity element is a partition of the group G. If either A with the identity element or B together with E is a subgroup of G, then Cayley graph GS is a divisible design digraph, and the right cosets of this subgroup give a canonical partition of this digraph. And again, as in this theorem by that I mentioned that at the beginning, we have also that conversely, if this Cayley graph GS is a DDD, then the class of its canonical partition, which contains the identity of G, is a subgroup of G, and classes of the canonical partition of DDD coincides with the cosets of this subgroup. Yeah. So we translated this theorem by Kabanov and Shalaginov to this setting. Again, we have first that obvious construction as similar to that or the same actually that we had for Cayley DDGs. So if A is an incidence matrix of a symmetric VK lambda design with a regular automorphism group G, and if A is skew, so now we have to assume that the matrix is skew, then there exists a divisible design Cayley digraph with parameters V times T, K, lambda, 0, T, and V. Again, we just take a canonical product of identity matrix and A, and this is a JCC matrix of DDD with these parameters, and then we have to conclude just that we have regular automorphism group, and it is obvious that direct product of G and the cyclic group of order T acts regularly on that structure, so we just conclude that this is a Cayley digraph. And again, so in this proof of theorem 9, instead of this identity matrix, we can use any permutation matrix P, and we will also get Cayley in DDD. So a direct consequence of theorem 9. Yeah, in this theorem, what we need just symmetric design with the skew incidence matrix. So we know that Paley designs are such designs. So we can use Paley designs for this construction, and let V be a prime power congruent to 3 modulo 4, and T be a non-negative integer. Then there exists a divisible design Cayley digraph with these parameters V times T, V minus 1 over 2, V minus 3 over 4, 0, T, and V. Yeah, okay, just as I said before, we just take Cayley design. We know that this is a symmetric design with skew incidence matrix, and then we use this construction, and we know also that that it is easily seen that the direct product of the additive group of the field of order V and the cyclic group of order T acts regularly on this structure. Yeah, now we have in theorem 10 we have also that obvious construction as in the case in the previous case of divisible design graphs. So if A is the instance matrix of a symmetric weak lambda design with a regular automorphism group G, again A has to be skew. Then there exists a divisible design Cayley digraph with parameters V times n, k times n, and k times n, lambda n, v, and n. Yeah, again, this is it's obvious that this is a DDD with these parameters, and also obviously this DDD admits a regular action of the direct product of the cyclic group Zn with the group G. And so we have Cayley structure. So again, what do we need here? We need symmetric design with the skew incidence matrix. So again, we know examples of such designs. Examples are Cayley designs, and we know that Cayley design exists for every prime power which is congruent to 3 modulo 4. So if we take any V which is prime power congruent to 3 modulo 4, and if n is a non-negative integer, then there exists a divisible design Cayley digraph with these parameters V times n, V minus 1 over 2 times n, V minus 1 over 2 times n, V minus 3 over 4 times n, V, and n. So yeah, I think that is not necessary that I repeat that. We just use this Cayley design instead of any design, and we see that this is a DDG, and we also from this construction, knowing the automorphism group of Cayley design, we just conclude that we have regular action on this structure, and by Sabidu's theorem, this is Cayley DDD. Okay, now again, this is construction. I will not present the proof here. It is not that easy and short. If V is a prime power congruent to 3 modulo 4, then there exists the divisible design Cayley digraph with parameters V squared, V times V minus 1 over 2, V times V minus 3 over 4, V minus 1 over 2 squared, V. So this is also construction since we have V congruent to 3 modulo 4. So this is also construction from Cayley design. And next construction from theorem 12. So now we use two Cayley designs. Let t be a non-negative integer such that 4 times t plus 3 and 4 times t plus 5 are prime powers. So then there exists a divisible design Cayley digraph with this set of parameters. Yeah. So also we have, since we have two prime powers which are congruent, so we have one. Actually, we have one which is congruent to 3 modulo 4, and one which is congruent to 1 modulo 4. So here, in the first case, we use Cayley design, and here we use Cayley graph, and combining instance matrices in some way, we get Cayley digraph with these parameters. Divisible design Cayley digraph. So this is also one construction from Cayley design, but from one particular Cayley design, which is very well known, the smallest symmetric, non-trivial symmetric design. So let t be a non-negative integer such that 4t plus 3 is a prime power. Then there exists the divisible design Cayley digraph with parameters 28 times t plus 21, 8 times t plus 7, 4 times t plus 3, 2 times t plus 2, 7, 4 times t plus 3. So this is based on this incidence matrix. So D is incidence matrix of Cayley design with parameter 731. So this is, as I said, this is smallest non-trivial symmetric design, and known as also the smallest projective plane, known as Fano plane. And let D1 be the incidence matrix of a Cayley design with parameters 4 times 3 plus 4 times t plus 3, 2 times t plus 1, and t. And then we construct, then we use this D1 bar, which is actually complement of D1, and then we take a matrix Kronecker product of D and D1 bar, and identity matrix Kronecker product of the identity matrix of order 7 and D1, and yeah, it is it can be checked that this is adjacency matrix of DDD with these parameters. And from this construction, it is obvious that, or it can be seen that this DDD admits a regular action of the direct product of the additive group of the field of order 4 times t plus 3 and the additive group of field of order 7. Yeah, so this is another construction. Also, we can use Cayley designs for this. So we T1 and T2 are non-negative integers such that 4 times T1 plus 3 and 4 times T2 plus 3 are prime powers, and then there exists the visible design Cayley digraph with these parameters. So again, we have in this case we have two Cayley designs, and then combining this design in some way, or it's or their incidence matrices, we get the visible design, which appears to be Cayley. And we have, I'll just mention one more construction. If V is a prime power, also congruent to 3 modulo 4, and n is an integer, which is greater or equal to 3, then there exists the visible design Cayley digraph with these parameters. So again, we use this Cayley design, and from that Cayley design we can build another divisible. So Cayley designs are very fruitful for construction of divisible design digraphs. Of course, this fact that adjacency matrix of Cayley design is Q is crucial here. And now this is construction of Cayley DDD with parameters A30142. So this is interesting in a way that here we directly applied this theorem, so it is constructed directly from the group, namely the quaternion group of order 8. So we take this group, quaternion group, and set S to be ijk. Then this set S satisfies this condition that elements, that if we take elements of S and their inverses, then intersection is empty, and also S times S to the minus 1 is equal to A plus 0 times B, so it is not, there is no B, plus 3 times identity element, and where A is this set here, and B is E bar here. So it is so here we can see that this E bar is an involution. So if we take union of B and identity element, we get a subgroup of G. So by this theorem, we have so the Cayley graph is a DDG, and the right cosets of B give a canonical partition of Cayley DDD with these parameters. Yeah, So this is another construction, and in this construction we don't use Cayley designs, so maybe it is good to see that there are also other constructions without Cayley designs. For every odd integer n, which is greater or equal to 3, there exists a divisible design Cayley digraph with these parameters for n, n plus 2, n minus 2, 2 for n. So we take circlet matrix with the first row, 0, 1, and all other are zeros, and so this is n times n matrix, and we take complement actually of that identity matrix, and produce, and then produce this matrix 4 times 4 block matrix, and it can be checked that this is a adjacency matrix of a DDD with parameters from theorem, and direct product of the cyclic groups Zn and Z4 acts regularly on that DDD. So this is another construction, and I will mention now construction from balanced generalized weighing matrix. So BGV with parameters V, K, lambda. So such a matrix over over a group multiplicative group G is a V times V matrix with entries GIG with and entries are from G union 0. Such that each row of W contains exactly K non-zero entries, and for every A and B from that set, which are not the same, so the multiset, which is written here, contains exactly lambda over cardinal number of G copies of each element of G. We'll consider only balanced, balanced generalized weighing matrices with these parameters n plus 1 and n minus 1 over a cyclic group of n minus 1 element, and where n is a prime power. Such a matrix W has 0 diagonal entries, and if the entries of W are assumed to belong to the finite field for the n, then transpose of that matrix W is actually minus W, and so we say that this is a skew matrix, and so there is a divisible design digraph with these parameters for each n, which is odd prime power. So this is a short proof, but I think that there is no need that I read it, and so in this theorem we say that this is DDD, and in all cases that we have checked by computer, these these structures are actually Cayley digraphs with these parameters, and that leads us to the following conjecture, which we didn't prove. Let n be an odd prime power, then there exists a divisible design Cayley digraph with these parameters. So we just have evidence obtained by computer. Yeah, and these are some results obtained by computationally. So these are designs for V which are less or equal to 27, and lambda 2 is between 0 and K, and lambda 1 is smaller than K. We got these results by computer. There exist divisible design Cayley digraphs with the following parameters, and also by computer we excluded some Cayley DDGs, so we found out that there are no Cayley DDGs with these parameters, and these parameters are feasible, of course. That's the point. So these are not some random parameters. And this is a list of proper divisible design Cayley digraphs. So we have a list for up to 27, but this is just divided to two tables. So this is a table up to 21. So we have all these feasible parameters and regular groups acting on such structures, and number of Cayley DDDs with these parameters up to isomorphism, of course. Yeah, and these are groups. So this is a list up to 27. Yeah. So okay, I have here some part on about codes also, but I think that I can skip that and finish here. And I'll just say that in July we're supposed to have this. We will have this conference, which is satellite in Rijeka, which is satellite conference of the 8th European Congress of Mathematics. So we still hope that it will be possible to have it here in Rijeka in person. Yeah. So if not, we will do it online, but we'll still hope. We are just, I think that we have a little bit more time to decide, and so it would be very nice if we can meet in Rijeka. Yeah. Thank you very much. Yeah.
Thank you very much for your talk. Thank you very much for this announcement about the conference. Are there any questions to Dean?
Can I ask a question?
Yeah, sure, please.
Dear Dean, very thanks for the nice talk. Yeah. And I asked about the spectra of divisible design digraphs. What you can say about this? Because it's very useful for investigation, for study divisible design graphs. Spectra is very useful. What about the spectra?
Yeah, we didn't study spectra. Yeah, I know that you are interested in it. We didn't study it, so it's open, so you can write a paper about it.
Thank you.
Okay.
I have a question.
Yeah, Misha, please. Yeah.
So you used many times for construction the Pele design, where the number of points is 3 modulo 4. Yeah. Is it correct to say that you can replace Pele design by any doubly regular tournament in this construction?
Yeah, it's possible. Yeah, you have to think, but it's quite possible. Yeah. But,
I see.
Yeah.
Okay.
Yeah.
Mm-hmm. Any other questions?
Can I ask a question?
Yeah, sure, please.
Then you have used non-prime powers of shape 4t plus 3 and 4t plus 5.
Yeah.
Do you know, are there many non-trivial prime powers of this shape? I mean, they are almost neighbors. The difference is 2.
Yeah.
And
twin.
of course, there are possible infinitely many such primes possible. But are there some non-trivial examples?
Some non-trivial examples. Are there? Yeah, of course there are some non-trivial examples, but yeah, of these. Yeah. For example, there are 7 and 9, and yeah. So you mean bigger? So I don't know for bigger numbers, but for smaller numbers, yeah, one can find. So I didn't.
For example,
take time to look at these bigger numbers, because we didn't actually investigate some special properties of these constructed structures. Yeah.
For prime powers, the difference 1, there is a theorem by Geronov that there are no many non-trivial examples. This theorem was proved possible in 19th century. And possible there are similar results for prime powers.
Prime powers.
I just haven't researched this question.
Yeah, I don't know at the moment, but I didn't take a look of such theorems. Yeah, I know about, of course, twin primes, but yeah, I don't know if there is. It's possible that there is some result on twin prime powers of also. Yeah, but at the moment I don't know. Yeah.
Okay, thank you. Are there any other questions? If not, then let us thank Dean again for this very nice talk, containing a lot of interesting constructions for DDG and DDD. And actually, I wonder, do you think, is it possible to have something like a characterization of all DDG or DDD?
Of all?
Yeah.
Yeah, I don't know. Yeah, maybe in a, yeah, it depends in which way. Yeah,
in which
way,
way
that,
yeah.
In the way, of course, in that way of theorem of Vladislav and our translation. Yeah, it is possible. But yeah, there are, in a way, there are, as you've seen, there are many constructions of.
Right, that's true. And I also wonder, you see, on the first day of this workshop, Edwin shows us, he introduced a lot of matrices, adjacency matrices for digraphs. So do you think, is it possible to use something from that matrices to get some new divisible design graphs or digraphs?
Yeah, I didn't think about that, but it's a interesting question. Yeah, of course.
Yeah, it is tricky question, of course, because there are many matrices, and you need to have some special properties, right?
Yes. Yeah, just have to pick some right property, which is natural generalization. Yeah, it's good question.
Who knows? Who knows? Yeah, maybe it would be possible to use. Okay, are there any other questions? Well, if not, then let us thank Dean again. Thank you very much for this very nice talk. And actually, in 2 talks, we come back to divisible design graphs because Dmitry Panasenko will give a talk on enumeration of divisible design graphs. So we will see some new results. Okay, thank you very much, Dean.